to the final session of this afternoon. There are 4 speakers. The speakers will be going in a slightly different order from the one advertised in the program. And we'll be starting with Mason Porter from Oxford Maths, who's going to be talking about multiplexing.
Okay, so thank you, Mark, and the organizers for the invitation. I've switched order with Alex, but once he also gives his talk, then the mean amount of hair will then come back to where it should be. Okay, so I want to give an introduction to multi-layer networks. So this is something that even if you haven't looked at it, you've probably seen it a lot as a buzzword in the literature, especially the last couple of years. And it's something that has, it's attracted a lot of attention in certain communities, and it's something that I wanted to convey as things that are interesting to study. So I'm concerned more with just getting you interested in these problems, work on it in whichever ways you think are interesting, but hopefully some of you who are not yet working on it will become interested. I'm currently at Oxford. I will be moving to mathematics at UCLA in the fall. We have a review article that we wrote a couple years ago, and there are some tutorial slides that go with the review article that we put on SlideShare for anybody who wants to go through that. In addition to our review article, there's another review article that takes a different perspective that came out basically at the same time. So it's good to look at both of them and just to get different perspectives. And then more recently, since there's been a lot of work on it, there's been some more specific articles on various topics, a subset of which I show here that have been coming out. So for example, there's been some work on, there's a survey and a perspective piece on spreading processes on multi-layer networks, and we're going to receive a talk about that from Alex in a couple talks. But there's also a survey on percolation models, a survey on evolutionary game theory, on structural diagnostics, and on a few others that I don't have listed on this slide. Okay, so this is our object. You can write it down this way, which is conceptually what I have in my head when I think of things like this. So you can have ordinary types of connections, say between node 1 and node 2. It can have a weight if we want to give it a weight. It can have signs, it can have directions, whatever you like. But we also have connections, say, between node 1 and it says itself, which means this is supposed to represent the same entity 1, but now it's on a different layer. Instead of being in layer A, x, this one is in layer B, x. Maybe A is 0.1 in time and B is 0.2 in time, and x is Facebook friends, and B is somebody following the other person on Twitter, or it could be many other things. You can have more than 2 types of layering. This is just a pictorial example with 2. You can also have edges that go, say, from entity 1 on layer A, x to some other entity, say 4, on B, x. So if you have, say, different subsystems, then entity 1 in one subsystem connected to entity 2 in another subsystem. If you want, and if you keep the labels, you can write it as a standard type of graph, potentially weighted, directed, and so on. But entity 1 here is showing up 3 times, and so if I ask a question about is entity 1 important, then if I'm thinking of this graph, I actually am asking a question about 3 nodes rather than a question about 1 node. So I find this perspective to be a useful way to think about this, right? But as long as you keep the labels, you can go here if you like. Okay, so one example is you put some sort of color on the nodes. This has some names. If you wanted to use that as a model of something, one possibility would be for a network of networks, so UK infrastructure. So for example, just to give a random UK example, sewage interacting with railways, completely random example. But the point is you have different nodes in these different subsystems, but they can interact with each other. And there are engineers who are trying to think about using these sorts of ideas to look at that. So this picture comes from my colleague Scott Thacker at Oxford. Another very common example, one that's been studied even longer, is called a multiplex network. The simplest type of doing it would be to just put some sort of color on the edges, color in the sense of a label, not in the sense of specific coloring rules. So for example, you might have different airlines, and so an intra-layer edge would be one flight of a given airline, but we know that there are different airlines that all operate in the same airport, so you might also need to go from one gate to another gate. That might take some amount of time. You can also have different types of social interactions. As I mentioned, you can have more than one type of layering at once. So for example, you might have points in time representing interactions that occurred at different conferences, and you might have different types of interactions at those conferences. Okay, so we're going to have a 4-tuple. You've got your set of entities, which is the same as we're used to. You've got sequence of sets of possible layers, and we use the term aspect for this dimensionality of layering. So d equals 0 will get us back to an ordinary network. D equals 1 says I'm layering in one way, say social connection 1, social connection 2, social connection 3, and so on. D equals 2 is an example that I showed you pictorially on the last slide, say both time-dependent and multiplex. And in principle, you can go as high as you want, though if you look in the literature, there's not so many that have gone beyond d equals 1 in terms of studies they've done. There are a couple that have done, say, multiplex and time-dependent. But you can imagine, there are ways you can imagine more. In addition to representing the entities and the sequence of layers, you also want to represent an entity on a specific layer. So you call this a node layer or node layer tuple. The idea is that VM says, here is a specific entity, and here is the layer that I'm looking at it on, because we know that this entity can appear multiple times. And you also have a multi-layer edge set, but what we're connecting with the edge set is node layers to other node layers. The node layers become the nodes if you go back to the representation of a graph that I showed you a few slides ago. So I will just show you this to remind you. So 1, A, X is a node layer, whereas 1 is the entity that is there, and there's 2 other copies of node 1. Oops, wrong one. And then if I want to have, again, if I want to have weights, I would have a mapping from the edge set, say, to the real numbers. If you look in the literature, there's a bunch of things that are various special cases of this with terminology that has become a mess. This is a subset of the terminology that you will see in the literature. These are all cases of what I've mentioned, but with various constraints that people have put in on what they're studying. You can also represent things in a linear algebraic way, using a generalization of an adjacency matrix. And there you've got, if you have an unweighted one, for example, you would put an entry of 1 if entity U on layering alpha is connected to entity V, or is adjacent to entity V on layering beta. You put 1 if it's an element of the edge set, but you put 0 if it's not. Now, if you're going to be working with a linear algebraic object, you have to worry about the dimensions matching. And in many of the papers, a very common assumption is to assume that all entities are present on all layers. We all know that there's tons of applications for which you really don't want to do that, right? So it's a simplification. It's helpful, but it's certainly not without loss of generality. So one thing that one can do if you want to deal with that is that you can pad layers with empty nodes so the dimensions match, but then you have to distinguish between edges that could have been there but are not there. So missing edges in the words from the ecologist, and forbidden edges, edges that are simply not allowed. And so if you're going to normalize something, you need to treat those differently. This is a major thing that's only really been worked out in a couple of examples, but it's important. Again, if you want to represent things linear algebraically, you can actually represent it as a larger adjacency matrix, which sometimes goes by the name of a supra-adjacency matrix. You want to keep the labels, although when I do my computations, the computer won't know there are labels. But when I'm asking questions of what I want to compute in the first place, I want to think about those labels. I have this reference here just because this particular figure comes from it. But in this figure, the on-diagonal blocks are the ones that refer to intra-layer edges. The off-diagonal blocks are the ones that refer to inter-layer edges, which in this particular case is nodes only connected to copies of itself with a constant weight omega. Okay, couple of I thought I removed most of those. Oh well. All right, couple of applications, not to go into any details, but just to hopefully help with the motivation. A good example, and one where actually getting data on the interlayer edges that you trust is a bit more reliable on this example, or maybe I should say easier rather than more reliable than on others, is from multimodal transportation networks. And there are some nice papers from Riccardo Galati and Mark Bartholomei, and occasionally co-authors, that have discussed them. And they've also released a bunch of their data to the public. I'm going to show you a couple of plots from one of their papers and just very briefly say something about it. This data set is from transportation in the UK. And they have some that's national, and they have some that's intra-cities. So in this one on the left, they have the distance in kilometers on the horizontal axis, and they have the fraction of all, I think it's either shortest paths or trips, time-respecting shortest paths or trips that cover that. And one of the things that you'll notice is that people only start flying if two cities are sufficiently far away. But you have other times where coaches are doing very well. Eventually, flying will dominate. So this is a nice empirical study. Another thing that they did, I think it's in the same paper, is this one on the right. This one is looking at at networks from different cities separately. So I think 13 different cities in the UK. These are time-respecting shortest paths, time-respecting in the sense that they actually looked at the schedules of when things were going and the amount of time they took, rather than just, say, measuring the distance from a map. And so this is that's that distance of a trip that's being used on the horizontal axis. On the vertical axis is how many modes on average. So say L equals 5 kilometers, how many modes on average in a given city are used for a 5-kilometer trip if you're doing a time-respecting shortest path. And so one thing you can see is that these curves for different cities are different from each other, suggesting, not surprisingly, that the urban transportation system of some of these cities works somewhat differently from each other. So it's an interesting way to look at it. Another application, and I only have this one slide on this because I want to get to something else, is in ecology. I was approached by some ecologists to write a perspective piece on them, which felt more or less like writing a review article before there were things to review. But you can have things like different patches, which would be having like different subsystems in space. You can, of course, have different points in time. You can include both what are called trophic and non-trophic interactions and so on. One particular paper that I find interesting that's been done in this area in the past is by Scotti et al. In Journal of Complex Networks. They had 3 layers. They had a population. They had a food web, which would be called in their language a community, but which is not the type that we've been talking about this week. And they would have patches in a landscape, which in their language would be a meta-community. And basically what they illustrated with their calculation is that the meta-community is sensitive to ecological processes that would occur of single species that are occurring on a different layer. So it gives a way of studying these problems, organizing it by different layers. In this case, you actually even have different levels in the sense of an interaction in one of these layers could imply something about an interaction in the other, right? They're not necessarily independent from each other. Okay. Another thing I wanted to give, that transition was on purpose, is to think about the notion of transitivity. I don't think clustering coefficient's been defined explicitly at this workshop yet, but it's one of the simplest measures of transitivity. And what you would do is you have person A friends with person B friends with person C, and you can ask how often are A friends with C, right? How often do you complete the triangle? The thing is, if you have entities that exist on multiple layers, the notion of completing a triangle is a little bit more awkward. So one thing that you could do is go back to entity 1 on the same layer, but another possibility would be to go back to entity 1, right? So you go back to the same entity, but you don't go back to the same entity on the same layer, so you don't actually have a closed path at the level of the graph, but you've still closed in some sense, perhaps if you're thinking about transmission of information. Right? And you can define these in different ways. You can ask, how often do I change layers? And so you have steps that are within a layer, which comes from an adjacency matrix. You have steps that are between layers, which comes from, say, a cross matrix. And so you can ask, you can try to generalize the question of, well, when do no triples close into triangles, except now I have to put triples in quotes, and I have to put triangles in quotes. Okay, so our point of view was to look at walks as the more fundamental object rather than cycles, because we're not necessarily going to be completing cycles when we do this, but you have walks with both intra-layer steps and inter-layer steps with different applications, as you can imagine from the example with transportation versus social networks. There might be different costs of changing layers in some applications versus others, so you want more than one way of defining these. And so we keep track of elementary cycles that traverse different numbers of layers. So you've got the A's are these block diagonal, or the blocks on the diagonal that I was showing you a few slides ago. The C's are actually the blocks on the off diagonal. We keep track of a matrix of a complete graph with no self-edges. This is useful for bookkeeping. And you can define different clustering coefficients by notions of triangles, now in quotes, divided by notions of connected triples, depending on how much you want to weight different types of steps of how many times you go layers you cross.
Can you give me an example of a node that is not connected to itself in another layer? What does that mean?
A node that is not connected to
I
itself.
don't understand what the connections between a node and itself are.
Yeah, so that's one of the trickier things.
Give me a real world example
of a node that's
not connected to itself.
A node that's not connected to itself.
Why aren't they just always connected?
I think most of the examples we study, we do always connect nodes to themselves. I don't think the answer is necessarily that it's not true, but in what we study, we normally do connect it to itself. But you could imagine that the connection to itself might have a different weight in different situations. For example, if it represents a transition probability of my posting something on Facebook versus my posting something on Twitter, different people could have different transition. So you can certainly imagine heterogeneous weights without a problem. Whether you can imagine it being 0 unless you make them all 0 and don't worry about it, I'm not as sure about. In transportation networks, you would also have situations where you would have different weights between, because that might represent how long it takes you to go from, say, one part of Paddington to another. And if you do that with Paddington versus King's Cross, those values could be different, right? So heterogeneity is easy to answer, but 0 versus non-zero is more of a modeling choice. Thank you for that. Okay, so we can put different coefficients on different sorts of moves, which end up on 3 different entities and returning to ourselves, but return to the same entity in various different ways. And there's a long paper that you can read if you want, but one thing that one can think about, suppose every layer with interlayer edges consists of Erdős-Rényi networks, or GNP Erdős-Rényi networks, and you define clustering coefficients in different ways by basically by putting different values on the coefficients that I was showing you on the prior slide. And so F and C are examples where P is 0.1 in layer 1, P is some value x, as shown on the x-axis in layer 2, and P is 1 minus x in layer 3. And so these two panels, C and F, correspond to different ways of defining various types of clustering coefficients. The stars are from numerical calculations, and the curves are numerical solutions of analytical. Yeah.
So the connections between different layers, are they also same?
So in this, I don't remember what we did for this one. In some cases, you put 0 just by saying I have different layers that are different, and I might put a correlation but don't have a value. I don't remember what we did for this one. The main reason I'm showing this slide is the fact that if I define my clustering coefficient in a different way, and for different applications I want to do it in a different way, things like Erdős-Rényi graphs are going to obey different curves as a function of the probabilities, ones that we gave approximate forms for analytically. And so given that there are different ways of defining a clustering coefficient, there were some papers in the literature that had just written down formulas as opposed to deriving it. Right? We started from walks and considered it, and they scale in different ways from each other. Okay, so the idea is that you have to consider it really carefully, and this is just one example with just one computation to illustrate that. But it's also one that if one wanted to go and do things in a more mathematical way, we have an approximation for those curves. In principle, one should be able to actually rigorously prove what those curves are in this case. Okay, how much time do I have? A lot?
12 minutes.
12 minutes left. That includes questions, right? No. Okay. So the other thing I wanted to talk about, I spent a little bit longer on the previous part than I intended, is measuring important nodes. And what I want to do is to do layers representing different time layers and to ask about important nodes that might change in time. So these are known as centrality measures with various different adjectives telling you how they do it. One type that's popular is hubs and authorities, which is a variant of eigenvector centrality that we've heard about. But in this case, you have both in edges and out edges. So something is I'm trying to get them in the right order. A good hub points to good authorities. So I've got out edges pointing to good things, and a good authority points to good hubs. You do this recursively, and you get an eigenvalue problem, which you can solve the left and right eigenvectors in order to get vectors that are the hub vectors and authority vectors. By Perron-Frobenius, I will have them with all components strictly positive, and then I can do a hub ranking and an authority ranking by the values of those components. One thing that we did very quickly a few years ago is use this to rank mathematics departments using data from the Mathematical Genealogy Project. Now, so far we are ignoring time dependence, and of course mathematics departments can change in quality over time. And the way that we defined edges for now, so give the example of Andrea Bertozzi. She got her PhD at Princeton. She later on advised students at Duke. So we're going to end up getting a directed edge from Princeton to Duke, but only in 1999, which of course is a few years after she got there. So there is a delay in the data in terms of when we see it. And we later on also have an edge from Princeton to UCLA. And if you want to do, say, a multi-edge, you can do it based on the number of students you have. And the idea is that a university should be a good authority if it hires students from good hubs, and a university should be a good hub if its students are hired by good authorities. Right, this is what we hope. If you visualize it, so hubs are the size of the node, authorities are color with blue at the bottom and red the most. You see some familiar names. So it looks like it's not totally crazy. You can compare the rankings to existing rankings. So we took the authority score, and this is the rank. Because we're doing the rank from bottom to top, if it's the same, it should then be the -1 slope line. There are some rankings from NRC in 1995, which are these blue ones. So there's some scatter, but seems to do OK. There are some rankings from US News and World Report in 2010. These are these triangles. Again, there's some scatter, but seems to do OK. The 2010 rankings are all over the place. Which there's a long story behind that, that's for dinner tonight. Well, yes, but there's a longer story than that. But it's interesting that you can see that with this simple calculation. But of course, we've thrown away time dependence, and we do know that the quality of various departments has changed over time. So we want to think about that. And so what we'll do is use one of these multi-layer networks where the layers are now time layers. We're going to define the time layer in terms of the year that somebody got their PhD. So Bertozzi, who got her PhD in 1991, is going to be a 1991 layer. That's how we did it. So directed edge from University I to University J from the PhD granted at time t. Multi-edges from multiple students will give weights. Those are intralayer edges. I haven't told you how to put a value on the interlayer edges, which is one of the issues that we often don't know how to do so much in this field so far. We have diagonal coupling in the sense of my connections between layers are only between corresponding entities in this particular case, and they're of some weight that I have not specified. We used 231 US universities. We went back 65 years, basically because of data sparsity. If you go back beyond that, we found that it's too sparse. And the approach that we took is to construct a version of a centrality matrix. So on the on-diagonal is a centrality matrix corresponding to any type of centrality you want, but it has to be a centrality that's expressed as an eigenvector of some matrix. So it will be the matrix corresponding to that eigenvalue problem. So for hubs and authorities, it would be the adjacency matrix at this particular time multiplied by the transpose. We have the interlayer edge weight started out as omega on these diagonal entries. We have just scaled it to put it as an epsilon, which is supposed to be small. And so we're going to do a singular perturbation from epsilon equals 0. Epsilon equals 0 would mean that I have an infinite weight between layers, which is morally a mean field type of assumption. And we're going to go for large epsilon, or sorry, for small epsilon, which means it's a large weight limit. And what you can do is then calculate order by order different centralities. So you start with a static centrality, and then you have the next order term, the coefficient of it would essentially be a first mover score, which the leading order says how much somebody moved. One nice thing about this, by doing the singular expansion, you can actually exactly solve the eigenvalue problem at the order 1. It's a known solution from several different fields, actually. So this is the eigenvector, this is the eigenvalue. You then do perturbation theory. I'm in Oxford Applied Math. Of course I do perturbation theory. And you can get closed form expressions for the coefficients of the perturbations. The main ones that we did numerically were just up to first order, but we showed the expansion a little bit more than that. Okay, so if you do this, the average, so this is the leading order term. Alpha is just a notation for the coefficient, and I don't remember which exact value of epsilon this is, but some value of epsilon for these numbers. You get a bunch of universities that you've heard of. First mover scores is a bit more interesting. You've got a couple universities and this is only showing the magnitude, not the sign. You've got a couple of universities that seem to, over this period of time, change more than others. So you see Georgia Tech, and you see CUNY. Now I have what, -1 minute? 2 minutes. All right, excellent, 2 minutes. So we decided to look at Georgia Tech, and in fact, one of our hypotheses before we started that calculation, 5 minutes. Wow.
You started a little bit after.
Okay. So, all right. Well, I guess I'm going to finish early, as it turns out. But one of our hypotheses before we started the calculation, a couple of us were at Georgia Tech a while ago, and we knew that Georgia Tech at some point made a transition from a teaching department, or a service department, to a research department, and so we actually felt that we would find that. We really did have this hypothesis before we did any calculation at all, and we were gratified that, in fact, this does show up in the data. So let's see. So we went into Georgia Tech in a little bit more detail in terms of doing calculations. There's important issues. For one thing, I think we heard in a couple talks the notion of localization. You can expect localization has to be something here that you're worried about because this is an eigenvector-based centrality. It's not something we deal with, but it's something that we point out as something that one should think about. Let me just go to the conclusions. Time for questions. So multilayer networks are something that I think is very interesting. I think there are good reasons to look at it. As I hopefully illustrated with clustering coefficients, and as I think you'll see in the next couple of talks, you have to think about how you generalize it, and there's going to be more than one way to generalize things, and it's going to be problem and data dependent. I think many real networks do have structures where it's meaningful to try to do this. One thing that came up in the questions is the notion of a value of an interlayer edge, and yes, that is an issue. In some applications, we have some understanding of what to do about that. So in multimodal transportation networks, you can measure how long it takes to go from one part of a station to another. In other networks, it's much less clear what the meaning is, so that's something that we need to work out more. As I said, there are specific examples where we're okay and others where we're not. Let's see, what else? You can throw away less data. I tried to give some motivation from transportation and ecology, and I tried to show a calculation for multilayer clustering coefficient, and in particular, different clustering coefficients because they do scale in different ways. So you need to check this when you're defining it. And then I talked briefly, maybe at lightning speed, about a temporal generalization of eigenvector centrality using a multilayer representation where the different layers represent a discrete time. We've got a bunch of public code if you want to play with it, although in this audience, I would expect you to want to try your own methods rather than use our code, but it's there if you want it, and that's it.
It looks like for a couple of questions. Nestor, why don't you come and sit up here?
So there's a gap for both of your scores between MIT and the rest of the department for the math.
Yeah.
Is that what people perceive MIT so much for the rest?
Well, I was an undergrad at Caltech, so I hope not. Aside from that, no, I don't know. I mean, it's true that this came out there with a method, but we were more trying to just sort of illustrate a proof of concept. I would not want to go claiming that I believe that MIT is that much better than the others. I wouldn't want to do that. But I agree that it's interesting that the computation suggests that. But we didn't pursue that further.
It seems like one issue with this centrality measure is that it rewards quantity in addition to quality. So that if you had a school with very few graduates, but they were always hired at very good places, and could you model that by normalizing by making your matrix stochastic? In the
so I agree that is in there. This is actually one of those where a school, like a small school like Caltech or University of Chicago, will get affected by it. I don't know what's correct, but I absolutely agree that depending on how you define your, this is more of a definition of the centrality measure, not with the interlayer, but even just of the centrality measure on the blocks. I think that's already present there. But I agree that is in there. And I'm not trying to claim that the hubs and authorities are the right one to use, but it was one that was meaningful to us in terms of the intuition of good people being hired at good places. And that's why we use that one. But yeah, so maybe the short answer is yes, that's there, but what is the best thing to do is something I don't know.
Any other questions? If not, let's thank Mason again.